Welcome. What you're about to watch is a preview of Part 1 of the book LLM Primer 3, Enhancing Enterprise AI with RAG, a practical guide to building retrieval-augmented generation systems for the enterprise, by Sho Shimoda, available on Amazon. If anything in this video resonates and you want to go deeper, the full treatment, every architecture, every trade-off, every production decision, lives in the book. Link is in the description. In this preview, we're going to take a structured look at the evolution of Retrieval-Augmented Generation, RAG, as an enterprise architecture. This isn't a beginner overview. We're going to walk through 4 distinct generations of RAG systems, the engineering trade-offs at each stage, and where the actually lives in each one. By the end, you'll have a clear mental model for picking the right architecture for the right problem, and you'll understand why so many enterprise RAG deployments stall out at the pilot stage. The diagram you see here is a preview of the territory, a neural query processor on the left, feeding an intelligence flow into a knowledge retrieval system on the right. Every piece of this gets unpacked over the next 17 slides. Let's start with why we need RAG in the first place. Before we can talk about RAG, we need to be precise about what large language models cannot do on their own. There are 2 structural limitations, and they compound. First, frozen knowledge. A model only knows its training corpus, and that corpus ends on a specific date. It has no mechanism to recall fresh documents. It produces statistical averages of past data. Second, zero provenance. Models generate tokens by statistical association, not citation. There is no internal bookkeeping that tracks where a specific fact came from. Combine these 2 limitations, and you get the failure mode every enterprise team has seen: confident, citation-laden fabrications. The model sounds authoritative. It even invents source names, but the underlying facts are wrong and unverifiable. This is not a prompt engineering problem. It's an architectural problem, and it's the problem RAG was designed to solve. Here's the core thesis of RAG, and it's important to state it precisely. Retrieval-augmented generation does not change the model's weights. It changes what surrounds the model. On the left, the before picture, a model trying to store thousands of documents inside its parameters. That's memory, and it's lossy, static, and expensive to update. On the right, the after picture, a small reasoning core with on-demand access to a structured external knowledge folder. The model becomes a reasoning engine, not a memory store. This gives you 2 enterprise-grade properties. Instant updates. You change knowledge by editing documents, not by retraining weights. And verifiable answers. The system fetches facts first, synthesizes second, which means every claim can be traced back to a source. That separation of reasoning from knowledge is the foundation everything else in this deck builds on. Now, the central organizing idea for this whole presentation. RAG is not one architecture, it's a continuum, and the dimension that matters most is where the intelligence lives. In stage 1, naive RAG, intelligence lives strictly in the model. The pipeline around it is dumb plumbing. In stage 2, advanced RAG, intelligence becomes distributed across engineered heuristics that wrap the retrieval pass. In stage 3, modular RAG, intelligence migrates into the routing, how components are connected per request. And in stage 4, agentic RAG, intelligence governs the entire loop. The LLM decides what to do in what order until the answer is complete. Each stage solves the previous stage's failures, but introduces new costs. Keep this continuum in mind as we walk through each stage in detail. Stage 1, naive RAG. What I call the napkin architecture, because the entire design fits on one. The flow is linear. Take a document, split it into chunks, embed those chunks, store them in a vector database, retrieve the top K by cosine similarity, stuff them into a prompt, send to the LLM, return the output. That's it. You can prototype this in a day with any modern framework. The kitchen metaphor is useful here. Imagine a librarian who grabs 5 books whose titles sound like your question and hands them to a fast-reading assistant with the instruction, answer this from these. That's exactly what naive RAG does. It works astonishingly well in demos. It produces a working chatbot you can show to executives in a week. And, as we're about to see, it has serious problems the moment you put it in front of real users. Here's why naive RAG fails silently in production. 3 failure modes, all of them invisible until users complain. First, Similarity is not relevance. The retriever finds documents matching meaning in vector space, but Apple earnings embeds mathematically close to Apple orchards. High cosine similarity, zero semantic relevance. Second, context loss. Fixed token chunking slices tables in half, separates pronouns from their reference, and breaks the self-contained units retrieval depends on. Third, multi-hop failure. Ask, summarize 3 agreements, and if the third agreement embeds slightly further away in vector space, it gets cut from the top K. The system silently answers with 2/3 of the facts. The takeaway? Naive RAG is an impressive demo. It rarely survives as an enterprise product. So the field responded by wrapping the pipeline with heuristics. That's stage 2. Stage 2, advanced RAG. The linear backbone from naive RAG remains intact. You still split, embed, retrieve, and generate. But the retrieval path is now surrounded by engineered heuristics that intervene at 2 points. Pre-retrieval. Fix the query before it ever hits the index. The user's raw query is often ambiguous, compound, or poorly aligned with how documents were written. Pre-retrieval reshapes it. Post-retrieval. Fix the results before they hit the model. The initial top K from vector search is noisy, redundant, and only loosely ordered by true relevance. Post-retrieval re-ranks and filters it down. The mental model is simple. Naive RAG was one shot at retrieval. Advanced RAG gives that single retrieval pass 2 chaperones, one on the way in, one on the way out. And that's usually enough to take a system from demo to internal tool.
Let's open up those 2 chaperones. Pre-retrieval typically combines 3 techniques. Rewrite removes ambiguity from the user query. Decompose splits compound questions like compare X and Y into independent subqueries that can each retrieve cleanly. Hide, hypothetical document embeddings, embeds a fictional ideal answer instead of the question itself, which often matches real documents better than the question does. Post-retrieval is where the biggest single quality lift in modern RAG happens. You retrieve a wide top 100 from the vector index, run it through a cross-encoder re-ranker that scores query document pairs jointly, dedupe near-identical chunks, and pass a clean top 5 to the model. The number to remember. Adding a cross-encoder re-ranker typically lifts top 5 relevance from 50 to 70% into the 75 to 90% range. That's a step function improvement, not a marginal one.
Stage 3, modular RAG. We now break the linear backbone entirely. Components are no longer wired in a fixed sequence. The pipeline is assembled dynamically, per request. A router at the top inspects the incoming query and decides which retrieval modality to use. A factoid lookup might hit a dense vector store. A precise number lookup might hit a structured SQL database. A keyword-heavy query might hit BM25 inverted indexes. The why is straightforward. A single retrieval mechanism cannot serve highly divergent use cases well. A factoid lookup requires entirely different machinery than a multi-document research synthesis. The cost, and this is real, is observability. When an answer is wrong in a linear pipeline, you know where to look. When the pipeline assembled itself differently for every request, the diagnostic signal becomes diffuse. You now require per-component traces just to debug a single bad response. Let's look at the anatomy of modular routing. The query enters a classifier router that decides intent, 3 common branches. Dense vector for semantic search, the conventional RAG path. Keyword BM25 for exact match queries where specific terms matter. Think product codes, error messages, legal citations. And structured SQL for relational data, queries that need to compute, aggregate, or join across tables. Each branch is its own retrieval subsystem with its own infrastructure. The interesting engineering problem is what happens when branches return results. You have to fuse heterogeneous outputs whose scores aren't directly comparable. The standard solution is reciprocal rank fusion, RRF, which merges results by rank position rather than raw score. The formula is simple. Sum 1 over k plus the rank in each list. The enterprise win here is significant. One unified codebase serves highly divergent query types without forcing every query through the wrong pipeline. Stage 4, Agentic RAG. This is the ultimate inversion. In naive, advanced, and modular architectures, The LLM is the last step in a pipeline. It receives retrieved context and generates an answer. In Agentic RAG, the LLM runs the pipeline. The diagram shows it clearly. The model sits at the center, surrounded by tools: search, SQL, calculator, web fetch, and it decides which tool to call, when, and with what arguments. The mechanism. The model is prompted with a catalog of available tools and their signatures. For each user query, it plans an approach, executes a tool, reviews the result, decides whether the answer is complete, and loops if it isn't. Retrieval is no longer a fixed step in a graph. It's one of many actions the model can take, on demand, as many times as needed. The pipeline has dissolved into a control loop.
Here's the power of LLM agency in concrete terms. Take a real query. Which EU vendors signed in Q3 and what is their average value? A linear RAG pipeline cannot handle this. It requires 3 different data fetches and a computation. The agent handles it natively. Step 1. Plan and decompose into subtasks. Step 2. Call vector search to find Q3 EU vendors. Step 3. Call SQL to fetch contract values for those vendors. Step 4. Call the calculator tool to compute the average. Step 5. Synthesize the final answer with citations. 2 capabilities unlock this. Multi-step planning. The model autonomously decomposes complex questions and fetches data incrementally. And multi-agent coordination. Orchestrator-worker patterns. Planner, retriever, critic, writer, where specialized agents hand off to each other. The kitchen metaphor. The chef reads the order, decides which stations are needed, and runs a station twice if the first pass failed.
But agency has a cost, and it's significant on 3 dimensions. Latency. Every tool call adds a network round trip and a model inference, and an agentic query may make 10 or more before completing. Cost. Where naive RAG cost you 1 LLM call per user query, agentic systems now consume 3 to 10 or more backend LLM calls for a single user interaction. Variance. The trace is no longer a fixed sequence. Pathological queries can flail endlessly in a tool loop, retrying the same failing action. The tech checklist is non-negotiable for production. Hard step limits on the planning loop, wall clock timeouts on the entire request, strict budget caps on tokens and tool calls. The rule of thumb you should walk away with? Do not use Agentic RAG for static FAQs. Reserve it exclusively for irreducible research complexity, where simpler architectures genuinely cannot get the right answer. Let's synthesize the 4 stages in one view. Naive RAG, embed retrieve stuff paradigm, intelligence in the model, low cost, best for demos and uniform documentation. Advanced RAG, heuristic wrappers, intelligence distributed across pre- and post-retrieval components, medium cost, best for standard enterprise knowledge bases. Modular RAG, composable graph, intelligence in the wiring between components, variable cost depending on query path, best for organizations with diverse query types they need to serve from one system. Agentic RAG, LLM as orchestrator, intelligence in the loop itself, high cost, best for complex multi-hop research where simpler architectures structurally cannot get the right answer. Notice the trade-off curve. As you move down the table, capability rises, but so does cost, variance, and operational complexity. There is no universal best architecture, only the right architecture for the workload you actually have. Now the question I get asked more than any other, should I use RAG or should I fine-tune? The framing itself is a myth. RAG and fine-tuning are not mutually exclusive alternatives. They solve entirely different structural problems. RAG leaves the model's weights alone. It changes the model's working memory at inference time by injecting retrieved context. So you use it when you have a knowledge problem. The model needs facts it doesn't have. Fine-tuning adjusts the neural weights themselves. It changes the model's vocabulary, style, and domain reasoning patterns. So you use it when you have a behavior problem. The model knows things, but produces output in the wrong shape, tone, or format. Treating these as a versus question leads to bad architecture decisions. The right framing is which structural problem am I actually facing? That's what the next slide makes explicit. Here's the diagnostic matrix to use when you're deciding. Knowledge problems on the left. The symptom: the model doesn't know the answer. Maybe the facts change weekly. Maybe regulatory requirements demand provenance on every claim. Maybe the data is highly regulated and can't go anywhere near the training set. In all these cases, reach for RAG. Iteration speed measured in minutes. You update a document and the system reflects the change immediately. Behavior problems on the right. The symptom: the model knows the right answer but produces it wrong. Tone is inappropriate for the domain. JSON output format is malformed. Domain reasoning style is unique and the base model doesn't match it. In these cases, reach for fine-tuning. Iteration speed measured in weeks. You label training data, run a fine-tune job, evaluate, iterate. If you can't articulate which side of this matrix your problem sits on, you don't have a problem definition yet. In production, mature enterprise systems eventually require both. The pattern has a name: RAFT, Retrieval Augmented Fine-Tuning. The recipe is 2 steps. Step 1. Fine-tune a smaller, faster model so that it perfectly follows your domain's strict formatting and reasoning patterns. You're teaching it behavior. Step 2. Use RAG to feed that optimized model the freshest facts at inference time. You're giving it knowledge. The model becomes a precise domain instrument fed by a current data pipeline. But there is a golden rule, and it matters more than anything else I'll say in this video. Always build RAG first. Enterprise failures are overwhelmingly knowledge failures. Wrong facts, stale data, missing provenance, not behavior failures. Most teams who jumped straight to fine-tuning ended up with a beautifully formatted model that still hallucinated the underlying facts. Solve the knowledge layer first. Add fine-tuning later, only if behavior remains the bottleneck. One final point to leave you with, and arguably the most underappreciated one in this whole space. We've spent 17 slides on architecture, but there's a ceiling above all of it, and it's not the architecture, it's the input. An agentic system with a state-of-the-art re-ranker is useless if your PDF parser flattened your enterprise tables into unreadable gibberish before any of this machinery ever saw the document. The architecture you choose sets the ceiling on RAG behavior. The document parsing you choose sets the floor. No re-ranker, no router, no agent loop can recover information that was destroyed at ingestion time. That's where the next layer of investment goes. Intelligent parsing, structure-aware chunking, table and figure preservation, layout-aware extraction. If you take one thing from this video, solve the data layer before you optimize the retrieval layer. That wraps up part 1. In the next video, we'll cover part 2, the data layer itself, how to parse, chunk, and embed enterprise documents so that everything we built today actually has something real to retrieve. Everything in this preview, in the full part 2 treatment, comes from the book LLM Primer 3, Enhancing Enterprise AI with RAG, by Sho Shimoda, available on Amazon. The link is in the description. If this video was useful, the book goes far deeper on every architecture we discussed. Thanks for watching. Subscribe so you don't miss part 2. See you in the next one.